Welcome to this next lecture on vibrations of plates and shells. We are in the topic of forced response, and we are looking at response of a simply supported cylindrical shell to a point harmonic force. So we reached this stage where we computed the axial response, response in the x direction. We are yet to find the u theta and u3. So if we continue, u theta is again summation I m n and f by rho h n m n I 1 sine m pi x star over L cos n theta star. Now the mode shape B m n I by C m n I sine m pi x by L sine n theta from the first set, and the minus that we should not forget, f by rho h n m n I 2 sine m pi x star by L sine n theta star, and again the mode shape from the second set B m n I by C m n I sine m pi x by L cos n theta, and the frequency term we should insert somewhere. Okay, so we'll close this first. One over omega mn square, etc., etc. Okay, again sigma I m n. I'll take certain terms outside, f by rho h. This can come out sine m pi x star by L. Then this also can come out sine m pi x by L, and B m n I by C m n I. Then I have cos n theta star sine n theta by n m n I 1 minus sine n theta star cos n theta by n m n I 2. Okay. Again here, when n equal to 0, okay, both these terms are 0. Both these terms are 0. Okay. Then from n equal to 1 onwards, n m n I 1 and n m n I 2 are equal. Okay. So we can say sigma I m n f by rho h. I'm sorry, I forgot the frequency term here. Omega mn square minus omega square plus etc. So we'll bring the frequency term here, omega mn square minus omega square plus, okay, sine m pi x star by L sine m pi x by L sine n theta minus theta star by n m n I first kind. Okay. And lastly we have u3, which is equal to sigma 3 terms 3 summations f by rho h n m n I 1, the modal force x star by L cos n theta star into the mode shape sine m pi x by L cos n theta plus force rho h n m n I 2, the second set modal force sine n theta star, the second set mode x by L sine n theta, and the frequency term 1 over there should be an I, sorry, there should be an I, omega m n I squared minus omega squared plus etc. Again, okay, we can see from here itself n equal to 0, this term is going to be 0. Okay, so if I do Imn f by rho h, this is common, this is common, so sine m pi x star by L sine m pi x by L into the frequency term 1 over omega square m n I minus omega square etc. into cos n theta star cos n theta plus sine n theta star sine n theta, this divided by n m n I 1, this divided by n m n I 2. Now in this term here, when n is 0, this term is 0 anyway, and therefore I can notionally make this n m n I 1 throughout. Okay, so the result is u3 x comma theta comma t. Okay, I have not been putting the temporal term, which is a mistake, so there has to be e to the power j omega t, e to the power j omega t everywhere, e to the power of j omega t yeah, it was here but later I dropped. That is equal to sigma I m n f, let me put by rho h sine m pi x star by L sine m pi x by L, the frequency term cos n theta minus theta star divided by n m n I 1. So that is the response of a simply supported finite length cylindrical shell with all components accounted for. Okay, I1, 2, 3 accounted for, both sets accounted for, okay, n, m, n, I1 and 2 accounted for, and so on, okay, the full blown. Now this is quite cumbersome every time, quite lengthy. In many shells, okay, let us say the aspect ratio is very long, that means the length is much longer than the diameter, then it turns out that in transverse or U3 direction shell is very flexible, shell is flexible and still stiff in axial direction and torsion, okay. So transverse displacements are high. And the other two direction can be ignored. Or if the shell is stubby, like diameter and the length are of similar order, then the axial and torsion natural frequencies are very high. Which means if we consider if frequency of excitation in the mechanical world is almost always in the range of less than 10 kilohertz, it is very difficult to get excitation above 10 kilohertz mechanically, unless you have explosions and cavitations and so forth. Those are rare events, but with gears rotating and pumps rotating and so forth, 10 kilohertz by energy comes down. Now these axial torsional resonances lie in the hundreds of kilohertz, okay, for stubby, this sort of shells. So what happens is these terms where you have omega m n I is equal to 1 and I is equal to 2, that means axial and torsion minus omega square, these sort of terms, because these are so high, the terms are for this particular I are small. So I1 and I2 can be ignored. So largely I1 and I2 can be ignored, especially if you are exciting in transverse direction, okay. We excited the shell in the radial direction, not in torsion nor in along the axis, Okay, we excited the shell in the radial direction. So displacements in ux and u theta can be ignored. I equal to 1 and 2 can be ignored. So dominantly u3 is composed of terms with I equal to 3. Okay, so u3 then will be equal to summation mn only, mn f by rho h e to the power j omega t sin m pi x star by L sin m pi x by L. Okay, and then we have the frequency term, which is just omega mn square, where these are I equal to 3 frequencies, omega square. Okay, and the of course the damping term plus etc. into cos n theta minus theta star divided by n mn. Okay, now n mn, let us see, we have integral 0 to 2 pi integral 0 to L sin square m pi x over L cos square n theta a dx d theta. Okay, so we have 1 minus cos twice m pi x by L 1 plus cos 2 n theta by 2, here also a 2 will come, a dx d theta. Now these will integrate to 0. Okay, so I have 1/4, I have 1/4 into a into twice pi into L. So this is L a pi by 2. Okay, for n not equal to 0. For n equal to 0, it will turn out to be L a pi. Okay. Similarly, for the other set, integral 0 to 2 pi, which we have already seen, sin square m pi x by L sin square n theta a dx d theta. So this gives me 1 minus cos 2 m pi by L by 2, and this gives me 1 minus cos 2 n theta by 2 a dx d theta. So this will go to 0, this goes to 0. Okay. Now when n equal to 0, this term is 0. Okay, and then when n equal to not equal to 0, we have the same L a pi by 2. Okay, so just as before, the same law holds over here for NMN. Okay, so for n equal to 0, it is L a pi, and not equal to 0, it's L a pi by 2. Okay, so this now is the reduced or simplified response of a simply supported shell. Okay. So now let's see. We'll do one more example here, which is let's say we have a traveling load. Okay, traveling load. On a simply supported shell. Okay. So we have a simply supported cylinder, cylindrical, let's say it's some angle, it's some theta equal to theta star. There is a load, okay, either upward or downward. There is a load that is moving. Okay, there is a steady load that is moving. So now we have Q3 x comma y comma t given by NF, okay, and delta at some angle divided by A and delta x minus Vt. Okay. As long as this force is on the shell. Okay. So V times T has to be V times T has to be greater than 0 and less than L. Okay. Then what happens? Then what happens is the Fmn, this time function of T, is 1 over rho h n m n integral 0 to L integral 0 to twice pi, okay, f delta theta minus theta star by A delta of x minus Vt. Okay, into sine m pi x over L cos n theta A dx d theta. We can put a heavy side to indicate that this can't exceed the length of the shell, but that's okay, notional. Once it exceeds the shell, it's a initial condition problem. Okay, so now this is 1 over rho h n m n f sine m pi Vt by L cos n theta star. So that is with set 1, let us say set 1. Similarly, you will have one with set 2, which is 1 over rho h n m n f sine m pi Vt by L sine n theta star. So I am doing the simple version here, okay. I am not taking all the modes, all the frequencies. This is the reduced version where transverse displacement dominates, okay. So then you have Fmn1, Fmn2, and so you have eta mn double dot plus twice zeta mn omega mn eta dot plus omega square mn eta mn is equal to f sine m pi vt by L cos n theta star. That is one set, okay. Then you have eta mn double dot plus twice zeta mn omega mn eta dot plus omega square mn eta mn is equal to f sine m pi vt by L sine n theta star, okay. So now you have to do a transient analysis with this as the transient force. And find the two eta mn's. So this is eta mn1, this is eta mn2, and then do eta mn1 sine m pi x by L cos n theta, eta mn2 sine m pi x by L sine n theta. Actually this has the look of a harmonic e to the power of j m pi v by L into t. So you could perhaps still try a harmonic solution where it changes with m, the frequency changes with every m, okay. You could try that. I have not done that, but it just occurred looking at the form, okay, and you can get the answer. So that is the moving line load, moving line load, okay. Now next, as we are talking of shells, I will give you one last example. So a line force, let me say a line force on a simply supported cylindrical shell. So what is it now? Again I will do a reduced version, okay, where only U3 is dominant. U3 is dominant, frequencies are only transverse, okay. Ux and U theta can be ignored. So the Q3 actually in this case is delta theta minus theta star at some angle. Then let us say F is the total force, then it acts over the total length or a fraction. Let us say it acts over a fraction from x2 to x1. This is force over unit length, and this is let us see, and then I set a Heaviside function h x minus x1 minus h x minus x2. So this is force per unit length, force per unit area, this is theta, okay. So this is force per unit area, units, so units are okay. Then the f m n, it's harmonic, okay, so it's harmonic. So now the f m n star, okay, is integral or 1 over rho h n m n integral 0 to L integral 0 to 2 pi f over x2 minus x1 delta theta minus theta star, this Heaviside function, okay, then sine m pi x by L, the first set, a dx d theta. So this Heaviside will pick the axial units limits as x1 to x2. Okay, so what we will get is 1 over rho h n m n cos n theta star integral from x1 to x2 sine m pi x by L dx. So this is taken care of, this is taken care of, this is taken care of. F by x2 minus x1, okay. Then the gamma mn 1 tilde is f by rho h n m n x2 minus x1 cos n theta star, okay. So this is minus m pi by L cos m pi x by L with limits x1 to x2, okay. Then frequency term 1 over omega square mn minus omega square plus okay. I hope I didn't miss anything. Then eta mn1 is gamma tilde mn1 e to the power j omega t, okay. Then eta mn should be multiplied by sine m pi x by L cos n theta and summed, and then summed over mn, okay. Now for the second set, okay, the second set, the same procedure will yield, I am just doing it this time, let us see, f m n star is, so let me call this 1, let's call this 2, integral 0 to L integral 0 to 2 pi f over x2 minus x1 delta theta minus theta star by A, this Heaviside function which limits the integral A dx d theta, second set sine n theta, okay. So this, and I have 1 over rho h n m n And so this becomes 1 over rho h n m n f by x2 minus x1 sine n theta star, and this integral from x1 to x2 sine m pi x over L dx. Okay. So then my straight away gamma mn2 is equal to 1 over rho h n m n f over x2 minus x1 sine n theta star minus so this should be yes, sorry, L over m pi. My mistake, L over m pi. So integral differentiation minus L over m pi cos m pi x over L x1 to x2 and the frequency term in the denominator omega mn square, etc. Okay. So if we put this together and get it back to eta, and finally the sum displacement x comma theta comma t, this thing looks like summation over m and n force by rho h n m n x2 minus x1, this term minus L over m pi cos m pi x2 by L minus cos m pi x1 by L into sine m pi x by L cos n theta minus theta star. Okay. Now what is this n theta minus theta star? We are getting it again and again. Okay. So what it is that at theta, if you have a cos n theta minus theta star, this is a maximum at theta equal to theta star. That means when you excite the cylinder, radially, let us say, then the mode aligns such that the maxima appears here, okay, at theta equal to theta star. The mode rotates, otherwise there is no location for an angular mode. Okay. This cos n theta and sine n theta can be oriented in any manner, but now that the force is at theta equal to theta star, the mode gets aligned to that forcing angle. That is what it means. Okay. I will close this lecture here. We will continue from here in the next class. Thank you.